Good afternoon, everyone, and welcome to this talk. So, just first challenge, how to go on. Okay. So, during this talk, I will describe a bit which are the applications for which we use RF front-end, the focus of this talk, and the innovation that we need for this technology, and which technologies will drive an innovation for these modules. So I will give you some examples of state-of-the-art RF front-end, and I will conclude with some perspectives and challenges for the future. So, 25 millions of US dollars. This is today the evaluated amount of RF module market in 2024. Shared among the following applications. So, in fact, first of all, we have consumer electronics, followed by wireless networks, automotive systems, military, and other applications, like, for instance, industrial automation. We have a lot of applications that we currently know in our life, like multi-band smartphones, or for instance, 5G MIMO systems, but also autonomous vehicles, collision avoidance, passing through military communications, electronic warfare, SATCOM, all space application, and diagnostic and instrument measurements. So a very important market for these modules. And as you can see, sorry, because I have not the same on the screen. And in fact, the prediction for the 2029 is still more impressive, because we will arrive at 42 US billions with an annual growth rate that is between 12 and 15%. So the driving application, the driving factors for this growth are mainly the 5G deployment, of course, the increasing use of a smartphone, but especially the IoT devices, the automotive industry, with in particular the autonomous vehicles, and the new Wi-Fi standards. Of course, there are some restraining factors too. For instance, first of all, the technology complexity, and after also all it is linked to cost and supply chains issues. How to overcome these factors and enable the technology, the innovation? First of all, we have also to work on the technologies. Driving the work towards higher energy efficiency, higher RF power and RF power density, but also higher frequencies, integration into the RF subsystems. For this, we have some challenges, like the effective thermal management solutions, and how to minimize the losses, mainly by co-optimizing the system through the design of the technologies and the system, and the heterogeneous integration that needs mechanical, metallurgy, and reliability issues still to be solved. The road to the next generation front-end, so from a technology point of view, is passing through going higher in frequency, for instance, by having new GaN technologies with reduced gate length to go upper in frequencies, up to exploring new technologies for the D band, but also through improving efficiency and integration. So we plan also to have second generations of technologies with more PAE and more power to cover the need up to the Ka band. Not only we need more integration, so there are second generation of both gallium nitride and gallium arsenide that has to be planned in order to add options for the compatibility with advanced packaging like hot vias, humidity protection, compact design, and of course we need advanced packaging technique to ensure an efficient heterogeneous integration. So let's go to check more in detail some example of advanced 3.5 technologies. For instance, here I put an example of what we can get in terms of higher efficiency. Here you can see that this is not a new trend in technology development, but it is more a leitmotiv of the last decade. So already, for instance, just taking the small example of UMS, we passed from GH25, the quarter micron technology, to the 0.15 in order to improve the efficiency, and we got 5 to 8 points of PAE. Now we target to improve still of 5 points of PAE with the new generation of GH15. And we can see that this is not something impossible to get, because we already have some results showing that this trade-off between performance and reliability, allowing higher efficiency, can be reached. After there is the trend to have higher power. Why higher power? Indeed, higher power density will allow to have smaller size, so higher integration in the system. And of course, we need, on the contrary, also to have a higher efficiency, because if we have very high powers, we will have big dissipating power, and we have to allow a good thermal management. So it is crucial to have also, for this kind of high power technologies, also very high efficiency. Here, for instance, we have GH25-20, the second generation of the quarter micron, that is targeting today more than 10 watts per millimeter. And this is totally possible to obtain, because we already had, for instance, today, some results at 12 watts per millimeter and more than 5 points more of PAE with respect to the first generation in the same voltage conditions. High frequency. So the need for the high frequency is mainly driven by the application needing high data rate communications link. That is not only for telecom, 5G, 6G, but also for all it is space, for instance, for inter-satellite links, and for defense, for electronic warfare, and for radar. In fact, when we go to high frequency, we can have higher radiation power, so we can increase the transmission range, and we can improve the power generation, the efficiency of the power generation, and by this reducing the prime power need. For this, in fact, we go we try to increase the frequency of our GaN technologies by reducing the gate length. So we have, for instance, GH10 up to the V band and the GH08 up to E band that are under development at present. You saw that we also can talk about the D band for 6G. For this, today the work is still ongoing because there are many unknowns to be solved before identifying the right technology to address these needs. But, okay, it is important to start looking around, especially to what the research laboratories are doing on this. The last point was to say, okay, we have to improve the wafer technology, but we have also to improve the integration in the RF subsystem. For this, in fact, we have, of course, the need to be compatible with the low-cost plastic package. That is the easier solution. But also, we are working on advanced packaging methods, allowing the heterogeneous integration of different technologies. So, gallium nitride, gallium arsenide, silicon germanium. And for this, for instance, we have some sample, let's say, platforms, like can be BGA for gallium arsenide and silicon, or also BGA with the top cooling for gallium arsenide and gallium nitride. But we can also have quite complex platforms going through the fan-out wafer-level packaging, so at 2.5 dimension or 3 dimension. But I will come back on this later. Just the important thing to say is that the wafer technology must be able to provide the right options to be compatible with this advanced packaging. So in particular, we need mechanical protection, humidity protection, especially for low-cost plastic package, but we also need hot vias, bumps, and this kind of features that can allow the flip chip and the high integration. So, in order to be more focused, to see better what we are talking about, I will go through some examples of state-of-the-art front-end modules made in UMS. And in fact, let's concentrate on high-power front-end for 5G application, because in fact, front-end can be very wide, as we saw before. So let's focus on the range between a few to tens watt of front-end for active antenna system, base stations, and transceivers. We see here a 5G phase array antenna, and this phase array antenna needs to cover multiple cells to ensure the links. And in fact, what we are talking about is just this module just connected to the antenna in charge of the transmission and of the reception of the signal. So let's also focus on the 3 licensed bands for the 5G. So we have the Ka band at 28 gigahertz and the 2 bands in Q band, the 37 gigahertz and the 39 gigahertz. In general, for the RF front-end for this application, the objective is to maximize the performances, to minimize the size and the costs. But of course, the trade-off between these 3 will depend on your application, and according to the right trade-off, there are several approaches that can cover this need. First, we can see, for the Q-band HPFE, in fact, in this case, the design drivers were mainly the performance and the size. So the decision was to design one single channel high power front end covering both Q-band bands, so 37 and 39 gigahertz. And in fact, in only one chip of GH15 technology in a QFN packaging. So in this one chip, we integrated 2 SBTD switches, the HPA and the LNA, in a very small chip. Here you can see the results of this work. So we had a very compact circuit, 2.2 by 2.6 millimeter square, packaged in a plastic QFN of 4 by 4. And from point of view of performances, we obtained 2 watt in a transmit mode with a gain between 23 and 25 dB and a PAE at the power peak of 12%. On the receive part, in fact, instead we had a noise figure of 4.5 dB with a gain between 24 and 26 dB. And these performances are a real state-of-the-art for Q-band TX-RX modules in package. So a very compact, a very performing product. And now another approach for the need is instead to use heterogeneous integration. So for this, I will more focus on this example for the Ka band, so for the bandwidth, the band 28 gigahertz. In this case, in fact, we combined the GaN power performances together with the gallium arsenide noise performances in order to have the best performances at module level. We realized then 2 chips. One in gallium nitride based on GH15 technology, where in fact we realized the SPDT switch and the high power amplifier, and another switch in another chip, in gallium arsenide and PH15, where we realized a self-biased driver and a self-biased LNA. Once that we designed this, how can we integrate these 2 different chips of different technologies and different thickness in one package? For this also we have several options. So first generation is the integration in overmolded plastic QFN. In this case, we got a 4 by 5 millimeter square package with 28 leads and with thermally enhanced die attach, because it is important aspect when you deal with GaN devices especially. And in the second generation, we used instead a topside cooled flip chip BGA package. I will come back on these performances later, just to say why we passed from first to second generation. In fact, the first generation, so the simple QFN package, had some limitation for the performances of the module, mainly due to the fact that we have bond wires, so the length of the bond wires to connect with the lead, but also the die-to-die distance can impact the RF performances. And after, another drawback of this package is the fact that the cooling is through the bottom side, through the exposed pad, and this can somehow complexify the PCB because of the thermal management. With the second generation, the main advantage was to easy the thermal management for the active antenna systems, because by means of the top cooling, we separed the antenna transmission on one side of the PCB and the thermal dissipation on the other side of the PCB. In such a way, the PCB is far less complex and more cost efficient, but it can also be reduced and be more compatible with the mesh size with a high frequency antenna. how it is realized. So here you can see the scheme of the schematic representation of this package. So you see the GaN chip and the gallium arsenide chip flipped down, and a heat sink on the gallium nitride backside in order to realize the topside cooling. We can also see that thanks to these connections through the bumps, we have the reduction of die-to-die to package pin distance, and we have it is also possible to reduce the die-to-die gap between the two chips. So the benefits thus are not only the separation of the thermal and electrical interfaces, as I already mentioned it, but also to have improved RF performances thanks to the shorter interconnections, to be able to do lower, smaller packaging because we can put the chips closer, and we can have thus a better integration in the antenna mesh size. The results, in fact, here you can see the picture. You can see that with this approach, we realized the 4 by 4 millimeters square instead of the 5 by 4 for the QFN. And from electrical performance point of view, we had in transmit mode the 2 watt with more than 30 dB of gain and a PAE superior of 24%, while on the receive mode, we had a noise figure of only 2.5 dB with a gain of minimum 18 dB. So very nice performances too. But it's not all. We have a third generation. The third generation, this is something more advanced in package, because we are always talking about heterogeneous integration, but this time we use techniques of fan-out wafer-level packaging to integrate the two chips. Why this? Because in fact, these techniques will allow to have higher integration and to of active and passive dies, even shorter interconnections, and we can mix all the technologies. And also in this case, we do the topside thermal contact. So I put here some results of this. We obtained, in fact, a package 4.8 by 4 by 3 millimeters square with both sides of 250 micron and a pitch of 500 micron. You can see here the schematic representation. So in fact, the connections are realized here by means of an RDL, so a redistribution layer. And so this is what allows to improve the performances and to by minimizing the losses. And also in this case, you have, of course, a top-side cooling approach with an integrated thick sink, heat sink to, for the thermal management. You see here the picture with the RDL well in evidence, and here the X-ray characterization. Unfortunately, I cannot show you the results because the characterization is still ongoing. But from the simulation, they were very promising. So you will have to wait for additional publications to see the results. And this will not be the end, because in fact there are still, we can always improve, there are still some challenges, and there is already a fourth generation that is on the table. And with the fourth generation, we will be able to do multi-channels modules with, by embedding active and passive functions, and it is what it is called package on package, SiP fan-out double-level package. That means that we will have a real 3D package in order to maximize the integration, minimize the losses, and maximize the performances. Just a last word is about the linearity, because in fact this is an important point not to be forgotten on the road to the integration, especially for telecom systems, because in fact in addition to enhance the performances, having a high linearity HPA can also greatly reduce the complexity of the system, because you can have a simpler or even no digital predistortion. And this is a very good point, especially if you have a very wide bandwidth systems, or if you want to improve the efficiency and the cost of your system. But also, in fact, the linearity will help to reduce the consumption of your HPA, because, in fact, it allows, in general, to use the PA at a higher PA. So here you can see, for instance, an example of a Ka band HPA of 25 watt with very nice linearity performances. So, in conclusion, in fact, we saw that today the innovation in wafer technology and also in the RF subsystem integration and packaging is driven by market needs for RF front-end in many applications and domains. We saw some example of heterogeneous integration in Ka and Ku bands with gallium nitride and gallium arsenide, or also very compact optimized solutions in one chip. And we have for the future still the evolution of front-end technology performances that can lead to have new generations of front-end modules, thanks to higher efficiency, higher power and power density, and higher frequencies. Of course, we can expect a big benefit by further exploiting the potential of heterogeneous integration to optimize the performances and the cost envelope. It remains some challenges on which we have to work. So, first of all, there are some challenges for wafer technology, especially for gallium nitride, for the optimization of performance and reliability with increasing frequencies. There are some challenges for packaging, because we have to minimize the parasitics and at the same time dissipate high thermal loss, also in fact with respect to the new wafer technology providing high power densities. There are some challenging from point of view on device modeling, because we need accurate large signal, noise, and high frequencies models, able also to predict electrothermal behavior of the devices. And we have challenges on product design, because in order to get an efficient RF front-end, we need a co-design taking into account the thermal, mechanical, and electrical performances of the different components. To overcome all these challenges, the collaborations are the best way forward, and because in fact the problems are multidisciplinary, and this is the reason why EuMS is participating and also leading several European programs to innovate in an efficient way in Europe. So, just last, a small thanks to all the colleagues who contributed close or far to this presentation, and to an overlook all the projects in which we are involved that contributed to our innovation. Thank you for the attention.
Okay, thank you, Valeria, for the very interesting and nice presentation. So indicating the next generation RF technology, heterogeneous integration, and roadmap for advanced packaging. So are there any questions from the audience? No? Yeah. So.
Hello, I am Giovanni from EuMIC. I ask, but I don't know if for confidentiality you can say or not, but I ask. What is the first challenge from all of the challenges that you plotted, that you showed? What is the first one that you would like to be solved? So let's say, if you have a wish, let's say in a dream, which one is the first one and why? Thank you.
Okay. There are let's say that I think that if we want to get industrial product, in fact, with this advanced packaging, the first challenge is to work on an industrial supply chain for packaging. And for packaging able to manage high dissipating power, because in fact we see that today we are able to obtain from wafer technologies good level of power density, but sometimes we have after to see beyond how we can manage them in the package and in the system. So I think this is a key point to allow, in fact, the industrialization and innovation in front-end modules to have this nice product on the shell. After there are many others, but okay, just to keep one.
Thank you. Thank you.
So we have time for more questions. Yeah.
Hi, thank you for the talk. I just had a quick question about the heat sink over the top of the GaN amplifier. How does that affect performance?
Sorry, the heat sink?
The heat sink in the BGA package of
yes.
the GaN amplifier, how does that affect the GaN amplifier, the performance of the package?
No, it will not affect the performances of the... This is the question, if it will affect the performances?
Yeah, it's just, I just expected with a heat
so this is this one. Yeah. In fact, when you go on this one, in fact, the fact of having, here you have your gallium nitride chip, flip chipped, and the fact of having the heat sink here on the back side, it allows to extract the heat from the backside, but on a different side with respect to the PCB. So this is the main use of this heat sink. The fact that the gallium performances will not be affected because it will have, how to say, it will not be impacted by self-heating because the cooling is working well. And for what is concerned the fact that it is flip-chipped, this is in any case simulated and taken into account in the design with respect to the height of the bumps and so on.
Okay, so let's thanks once again the speaker.
Thank you.